And one of the questions that we hear from our users is how my application will perform in APL64. Finding ways to optimize APL64 operation performance is one of our team's top priorities. In this session, we will discuss the performance aspect of APL64 and how applications may benefit from APL64's strengths. When discussing APL64's strengths, we need to revisit the product's design goals. APL64 aims to run on a 64-bit operating system environment, provide a much bigger workspace than APL plus Win, support variables larger than 2 GB, and make running on a non-Windows platform possible. Here's an example that shows that APL64 can allocate a much bigger workspace than APL plus Win. Workspaces in APL plus Win are limited to approximately 3.7 GB. Depending on users' provided environment, the actual workspace size may vary. So this is an example that I did on my machine with my configuration. So based on different configurations, the numbers may differ. In this example, we shows that we can create 3 variables. Each of these 3 variables exceed 2 GB. APL64 applications can take advantage of large workspaces and arrays. Our internal testing found that for large arrays, APL64 usually performs better than APL plus Win. This graph shows that test results for floating number addition. As we can see, for large arrays, APL64 performs better than APL plus Win. Similarly, this graph shows that APL64 performs better than APL plus Win when testing the integer division operation. For smaller arrays, our testing shows that some of APL64 operations are faster than APL plus Win. Some are comparable to APL plus Win, and some have potential to be improved further. We recently added a new tuning property called TuneDS. This property currently applies to addition, subtraction, multiplication, and division operations. When the array size is smaller or equal to the value of TuneDS, the interpreter uses a standard algorithm to process the operation. When the array size is larger than the value of TuneDS, the interpreter uses a native code algorithm to process the operation. The native code algorithm only works on a Windows operating system. The standard algorithm can be run on Windows and non-Windows systems. Our developer team considers implementing a native code algorithm when proven to be faster than a standard algorithm. APL64 developer may query or modify the system function setting to optimize system performance in an application system. The default value for the TuneDS is 100. Even though a native code algorithm generally performs better than the corresponding standard algorithm, the setup overhead for smaller arrays may offset the benefit of using a native code algorithm. So this screen shows the syntax of using this setting. So the developer can query and modify its value. And you can find detailed information in the documentation as well. This graph shows that adding smaller floating point number arrays is slower in APL64 than in APL plus swing when the tune DS is set to 0. So if we focus in this area, oops, sorry. So you can see for smaller arrays, when the tune DS is set to 0, the APL64 performs lower compared to the APL plus swing. When we change the value of tune DS to 100, the performance for the smaller arrays improved. We can see through this graph here. It's more comparable to APL plus swing, and in some cases, slightly better than APL plus swing. Here's another example of using tune DS setting. When the tune DS was set to 0, dividing smaller integer arrays was slower in APL64 than in APL plus swing. When we change the value of tune DS to 100, the performance of dividing smaller integer arrays was comparable to APL plus swing. So this shows the effect of setting the tune DS value. It has an effect on the performance of smaller arrays. But remember, currently, this setting only applies to addition, subtraction, multiplication, and division operations. While our developer team actively seeks ways to optimize APL64 operation performance, we encourage our users to use the quad profile function to send us profiling data. The quad profile is an excellent tool for profiling performance hotspots. It can be used to profile a whole function or within a function. For applications that include graphical user interface, the quad profile can be added in event handlers. Focused profiling can more accurately reveal performance bottlenecks. This is the example we received from our users. The profiling the test function shows the catenate into and epsilon functions were slow. This is actually a special case epsilon function, with the left argument being a vector, a character vector, and the right argument being a character scalar. So those two functions were over here. As we can see, they are on the first and the second on the list. After our developer team made a breakthrough in implementing the relevant functions, profiling the same function showed that catenate into was no longer the first item on the list. As we can see here on the left-hand side is the original profiling result, and on the right-hand side is the result after we make the modifications. The catenate into used to be on the first item here on the list, and after we make the changes to the functions, it's no longer on the first item. And actually, when we look carefully, it was not even on the top 200 of the list. And our developer team also optimized the special case epsilon function. The comparison of the profiling results showed the total time decreased significantly. The execution time for the epsilon function also reduced significantly. Here's the total time. After the modification. And so this is the catenate into, but we're not able to see it here. So for the special case epsilon function, yeah, we can see the time used to be this much, and now down to this much. Here's another user case. The user also sent us a more test workspace, and the test result shows the power, binomial, and decode functions were relatively slow compared to APL plus swing. This is the APL plus swing result, and this is the prior version of the APL64, and the binomial here. Oh, sorry. And the unit is milliseconds here, the decode function. And we could see those numbers were definitely slower, much slower than APL plus swing. After analyzing the APL64 implementation and test data, our team found that the slowdown occurred when the computation results require a promotion from integer to floating point number. After our developer team made the necessary changes to the functions, profiling result shows the performance of the affected functions was comparable to that of APL plus swing. So again, this is still the APL plus swing result, and this is the modified function in the newer version of APL64, and binomial here. The right hand side is binomial function. And the decode function used to be this much. Now it's like that. So yeah, performance optimization is an ongoing process, and your feedback will help us identify the areas to focus our efforts. Profiling the performance bottlenecks using quad profile could be a helpful step. So we just want to advise our users to use the quad profile functions. So this will help us to identify the areas that needs improvement and make the product more useful for us, for all the people. So this concludes my presentation, and thank you for your participation. And if you have any questions or comments, feel free to let us know.